Have you ever noticed your EV charging at 220 kilowatts, only to slow down to 70 kilowatts or even less after 80%? Many drivers think something is wrong with the charger. In reality, your battery is protecting itself, and understanding why could add years to your battery's life. To understand the slowdown, we must look at how energy enters the pack. Charging power, measured in kilowatts, represents the rate of this transfer. Standard alternating current from the grid cannot be stored directly. It must pass through the vehicle's onboard charger for conversion. This component is small and thermally limited. Direct current fast charging bypasses this bottleneck entirely, moving the massive conversion equipment into the station to send power straight to the battery. Yet, a charger's maximum rating is merely a ceiling. Power entry constantly shifts, raising a critical question. What commands the vehicle to throttle this current? Inside the pack, energy storage relies on two host materials. To charge the battery, lithium ions must be extracted from the cathode's chemical lattice. These ions travel through the liquid electrolyte to the graphite anode, while electrons are forced through the external circuit. At the anode, the lithium ions slip between the microscopic carbon layers of the graphite. This physical migration is called diffusion, and it becomes increasingly sluggish as more lithium accumulates inside. At the same time, the cell fights back with internal resistance. This resistance has three distinct parts: the liquid electrolyte's basic opposition, the physical barrier of crossing into the graphite, and the slow movement within the solid electrodes themselves. Pushing electrical current through these resistive barriers generates heat. As the graphite layers fill, fewer vacant storage sites remain. It takes more effort to force the remaining ions into place, driving up the individual cell voltage toward its absolute physical limit. To manage this rise in voltage, chargers employ a two-part process. During the first phase, known as constant current, the station delivers a steady flow of amperes while the battery voltage climbs. This is when the vehicle accepts its highest power, rapidly raising the state of charge, the estimate of usable energy stored inside the pack. But a battery cannot absorb this level of current indefinitely. Every chemistry has an absolute upper voltage ceiling. For lithium nickel manganese cobalt, or NMC, and nickel cobalt aluminum, or NCA, this limit commonly approaches 4.2 volts per cell. Lithium iron phosphate, or LFP, operates at a lower range, peaking around 3.6 volts. As the cells approach these physical limits, the charging strategy must shift to the second phase: constant voltage. To prevent exceeding the safe threshold, which would cause severe voltage stress and excessive heat, the system holds the voltage steady while forcing the current to taper off. Because charging power is the product of voltage and current, this drop in amperes causes the overall charging rate to plummet. This transition typically begins around 80% state of charge, serving as a common planning reference rather than a universal switch point. It explains why charging from 10 to 80% is incredibly fast, while filling the remaining 20% takes disproportionately longer as the current slowly trickles into the nearly saturated cells. This leaves an open question: what hardware actually directs this precise decay of power? The orchestrator of this slowdown is the Battery Management System, or BMS, the electronic control layer built on Gregory Plett's framework. Operating under UNECE Regulation Number 100, the BMS monitors individual cell voltage, temperature, state of charge, and state of health, which represents the pack's remaining capacity compared to when new. Because a single cell can limit the entire pack, the BMS continuously calculates the maximum safe current, communicating this live request to the station via ISO 15118 and IEC 61851. When charging slows, the station is simply obeying the vehicle's protective command, a process detailed in Episode 2, Battery Management Systems Explained. This aggressive reduction in current targets a severe degradation risk known as lithium plating. When an electric vehicle fast charges at a high state of charge, lithium ions flood the graphite anode. If the rate of incoming ions exceeds the anode's physical capacity to absorb them, the electrical potential at the anode surface drops to 0 volts relative to metallic lithium. Instead of sliding safely between the graphite layers, the ions deposit on the surface as metallic lithium. Over time, some of this metal detaches to become electrochemically inactive dead lithium, permanently locking away usable capacity and raising internal resistance. Under extreme conditions, these metallic deposits can grow into needle-like structures that risk puncturing the separator, causing an internal short circuit. Slowing the charge near 80% is a deliberate defense against this destructive reaction, an electrochemical bottleneck explored in depth in Episode 3, Lithium Plating Explained. But current is only half the equation. Temperature is the next major variable governing how much power a cell can safely accept. Inside the cell, temperature governs the speed of the chemical reactions. In a cold pack, lithium-ion movement slows and internal resistance climbs. Attempting to force high current into cold cells risks immediate lithium plating, so the battery management system limits the incoming power. Conversely, excessive heat accelerates degradation. If cell temperatures rise, the system must throttle the current to protect the pack from thermal stress. For many designs, maintaining a temperature between 20 and 35 degrees Celsius provides the ideal window for fast charging. To reach this sweet spot, modern vehicles use active preconditioning, drawing energy to heat or cool the battery pack on the way to a charger. In models from Tesla, Porsche, BMW, and Mercedes-Benz, entering a fast charging station as a navigation destination triggers this thermal preparation automatically. Hyundai and Kia employ similar route-based conditioning, although exact operational parameters and thresholds vary by model year and should be verified in the owner manual. While preconditioning consumes energy during the drive, it significantly reduces waiting time. Yet, even when preconditioned, vehicles parked side by side at the same station often produce remarkably different charging curves. These differences stem from system architecture and cell chemistry. While 400-volt vehicles like the Tesla Model Y, BMW i4, and Mercedes EQE dominate, others adopt 800-volt systems. At equal power, an 800-volt architecture found in the Hyundai Ioniq 5, Kia EV6, or Porsche Taycan halves the current. This lower amperage reduces cable mass, connector heating, and resistive losses, enabling high peak power. Yet 800-volt cannot bypass fundamental cell limits. Peak power remains a brief capability rather than a session-long rate. The resulting curve depends heavily on battery chemistry. Energy-dense NMC or NCA chemistries in the Model Y require careful upper voltage tapering to prevent degradation, resulting in a steep decline. The BYD seal utilizes LFP blade cells, which exhibit a flatter voltage profile and sustain power deeper into the charge. Every measured comparison reflects a precise combination of model year, battery variant, software version, and operating temperature. To charge like an engineer, use overnight AC charging up to your vehicle's recommended limit, 80% for nickel chemistries, or 100% for LFP. On long trips, activate route-based preconditioning and unplug near 80% to avoid the slow charging tail. This practical guide builds on our full series. Episode 1, AC and DC Charging Explained. Episode 2, Battery Management Systems Explained. Episode 3, Lithium Plating Explained. And Episode 4, Battery Chemistries and Charging Curves Explained. While future silicon anodes and solid-state electrolytes promise to shorten this final tail, today's slowdown remains a necessary shield. The more you understand your battery, the longer it will take care of you. Subscribe for more engineering-focused EV explanations. Engineers are already targeting the physical boundaries of this charging limit. Silicon-rich anodes offer a significant leap in storage capacity, though managing the material's 300% volumetric expansion during cycling remains a major mechanical hurdle. Advanced liquid electrolytes and wider 800-volt system adoption will help sustain higher power safely, while the emerging megawatt charging system prepares to deliver ultra-fast rates to heavy-duty commercial vehicles. True solid-state batteries, which replace liquid electrolytes with solid alternatives, represent a future milestone reserved for a dedicated upcoming episode, though commercial scaling remains years away. Today, fast charging remains a delicate balance between speed and preservation. As battery technology evolves, understanding this chemistry is what empowers us as drivers. The more you understand your battery, the longer it will take care of you. Subscribe for more engineering-based EV explanations.